Right? So either about the population mean or the population proportion. So the first thing we need to do for the hypothesis test is to state the hypothesis, right? So we say we want to state our claim. That's what do we want to test in our alternative hypothesis. That's why our alternative hypothesis have three options, either the right tail, the left tail, or two tails. Right, the null hypothesis will be always about the equality, right? We are testing about the same claim value in the alternative hypothesis, right? So we say for the population proportion or for the population mean, we have these three options, right? And then we call this P0 or this mu0, we both called our claimed value we want to test in our hypothesis. Right? And then we say after we state the hypothesis, we calculate the test statistics. We say if we are testing about the population proportion, then we have the z-test statistics, which is equals to p hat minus p0 over square root of p0 q0 over n. Right, we call this bottom as the standard deviation of the p hat. Right, and then here this p0 is our claimed value in our hypothesis. Right, so we say for the population proportion, quite easy. We just have this formula for the test statistics. But if we are testing about the population mean, then we need to be careful about whether this population standard deviation sigma is given or not given, right? So we say if the population standard deviation sigma is given, then we still have the z-test statistics, which is x bar minus mu sigma over square root of n. Right, so we still have this z-test statistics. We call the bottom as the standard deviation of x bar, right? But if the population standard deviation sigma is not given, is unknown, then we do not have the z-test statistics anymore. We have the t-test statistics, right? And then at the same time, since we don't, here, mu0, since we don't know the population standard deviation sigma, then we use the sample standard deviation instead. That's why we cannot call it as the standard deviation anymore. We call it is the standard error. Right, in your MyStatLab homework, sometimes they ask for the standard deviation, sometimes they ask for the standard error, right? So don't get confused, right? So we say if we are testing about the population mean, you need to be careful. You want to use the z-test statistics or the t-test statistics because this is, we say this is a very, very important step because next step we need to decide the p-value from either the normal standard normal table or the t-table. Right? So we say if you have the z-test statistics either from this formula or this formula, right? If you have the z-test statistics, you need to go to the z-table or we call the standard normal table, right? The other case for this case, when the sigma is unknown, if you have the t-test statistics, that means you need to go to the t-table to find the p-value, right? So we say the third step, find the p-value based on our test statistics. If you have the z-test statistics, we need to think about these three options, right? So we say if you have a right tail hypothesis, then your p-value will be the probability to the right of your z-test statistics, right? So that means once you have the z-test statistics, you go to the standard normal table, find the corresponding value. That value is the probability to the left. Then your p-value will be 1 minus, right? Because we need to find the probability to the right as the p-value. Second case, if you have the left tail hypothesis, then your p-value would be the probability to the left, right? So you use a z-test statistics, go to the standard normal table, find the corresponding probability. That probability will be your p-value, right? Because it is already the probability to the left. You do not need to subtract from 1, right? And then the last case for the two-tail hypothesis, then you need to be careful because now we care about the two tails together, right? So that means you can either find this tail times 2, or you can use this tail times 2 because it is symmetric, right? So normally, right, it's not always. Normally, if you have a positive z-test statistics, it would be more convenient for you to use the right tail and then times 2, right? If you have a negative z-test statistics, then finding the left tail will be more convenient, right? So it depends on you. It doesn't matter which way you like, right? Just find these two tails will be fine, right? And then next, if you have a t-test statistics, that will be, I think, that will be easier because you don't need to care about the right tail or left tail, right? And if you have a t-test statistics, you don't need to care about this test statistics is a negative value or positive value. You always make the absolute value of the t-test statistics, right? And then check your t-test statistics from the t-table, right? So we say from the t-table, we have the vertical axis as a degree of freedom. So that means we need to first fix the line of degree of freedom, which is n minus 1. So suppose this is my degree of freedom line, right? And then you can find your t-test statistics is between two values in this line. Then you go up to the top axis and then you have the range of your p-value, right? So we say if you have the t-test statistics, you can only get the range of the p-value from the t-table. But that will also be enough for you to make the conclusion. All right, once we have the p-value, the next step will be our conclusion, right? So we say we make the conclusion based on this rejection rule, right? So we say if the significance level, we call the alpha as the significance level, right? So we say if the p-value you got from the last step is less than our significance level alpha, then we reject the null hypothesis. Then we have enough evidence to support our claim. Okay, the other way, if your p-value is larger than our significance level, that means we do not reject the null hypothesis. That means we do not have enough evidence to support our claim, right? So actually, the last step is our conclusion. You either support your claim or you do not support your claim. You never change your claim, right? So for example, if you are testing about mu equals to 60, mu less than 60, right? You can either support that the mu is less than 60 or you do not support that the mu is less than 60. You can never make the conclusion about, okay, I do not have enough evidence to support mu less than 60. That means I have enough evidence to support mu larger than 60, right? We do not care about whether mu larger than 60 or not. We just care about mu, whether we can support the mu is less than 60. All right. Okay, so that will be all 4 steps. And let's go through an example. All right, so this example is about the mean rental car mileage. And we say that in the United States, the average car, the average car is driven about 12,000 miles each year, right? The owner of a large rental car company suspects that for his fleet, the mean distance is greater than 12,000 miles each year. He selects a random sample of n equals to 225 cars from his fleet and finds that the mean annual mileage for this sample is 12,375 miles. And the sample standard deviation is to be S equals to 2415 miles. All right. Okay, so this is the question with all information here. Right, let's read one sentence by one sentence. Right, first, in the United States, the average car is driven about 12,000 miles each year. Right, so this is the description about the population, right? Okay, next, the owner of a large rental car company suspects that for his fleet, the mean distance is greater than 12,000 miles each year. Right. Until here, what you can get for the hypothesis test. This sentence tells you Cole.
It tells the alternative hypothesis.
Perfect, right? So this sentence tells us the alternative hypothesis, tells us what do we want to test, right? What do we want to test? We want to test whether the mean distance is greater than 12,000 miles, right? This is what we want to test. So how we can state that? First, we need to decide it is about the mean, not about the proportion, right? So that means we are testing about the mean. Next, we want to test whether the mean distance is greater than 12,000 miles. That will be our alternative hypothesis, right? And then correspondingly, the null hypothesis will be mu equals to our claimed value, right? So in this case, actually, we are done with our first step, right? Our first step is already done. State the hypothesis, right? Next, they say he selects a random sample of n equals to 225 cars. So that means we have, what is n again? Sample size, right? So we have the sample size n, 225, from his fleet and finds that the mean annual mileage for this sample is 12,375. So what is this 12,375 miles? What is that? Justin?
X bar.
X bar, right? So this is the sample mean, the mean for this sample. So that would be the X bar, 12,375 miles, right? Okay, so next, the sample standard deviation to be S equals to 2415. So that means we know the sample standard deviation, 2415. Right. So in this case, the sample standard deviation is given. What about the population standard deviation sigma? Is known or unknown? Gia?
It's known.
Is known. What is the value of the sigma?
Is it the 2,415?
It's 2,415 is the S, right? We just figure out it is the sample standard deviation, right? So what is sigma? Sigma is the population standard deviation, right? So in this case, the population standard deviation is not given. we don't know the population standard deviation, right? Instead, we know the sample standard deviation, right? So that means sigma, unknown. All right, so in this case, if sigma is unknown, be careful. We can only have the t-test statistics. We do not have the z-test statistics anymore because the sigma is unknown, right? Okay, so next, step 1 done, right? Step 2, we need to calculate the test statistics. Right, remember, before you calculate anything, before you use any formula, right? All the formulas are based on our assumptions, right? Some of you forgot to check the assumptions in the last assignment, and I don't want to see that again. All right, so before you use any formula, all these formulas are based on the assumptions. All right, so be sure to check the assumptions. In this case, we need to check the independence assumption, normality assumption, right? So the independent assumption, the first thing, randomly selected, right? So we say the sample is randomly selected here, right? So it's checked. Next one for the independence assumption, 10% condition, right? So there is no population size here. How you can check your 10% condition? We say for the 10% condition, this condition is always true except 2 cases. The first case, if your population, you know your population is too small, right? Then this 10% condition is not right. Or if your sample is too large, for example, your sample is, for example, 2,000, 3,000. For this case, you need to care about the population size and see whether it is truly less than 10% of the population size, right? If there's no this kind of 2 cases, right? This 10% condition, normally this 10% condition is checked, even though the population size is not given to you, but it says it is a large rental car company. So of course your population size will be large, right? Sometimes it's about the United States. Of course, the population is large, right? Sometimes it's about a program. So of course, a program will be, the population size will be large, right? So all of these cases, this 10% condition, you don't need to worry about it, right? So
I have a question.
yes.
So for that 10% condition, I think on the problems for the essay assignment, on one of them, I think I might have said like, we assume that whatever the number was is less than 10% of like that entire population. For this problem, could you have said that? Like, could you say like, we assume the sample size of 225 is less than all of American cars? Could that work or no?
We do not assume. So we didn't assume this assumption is checked. We just say, since the population is large, that's why our assumption is checked. So we do not assume the assumption is right. You see the difference?
Okay, yeah, I see the difference.
Okay, perfect. All right, so you still need to give some details about why this assumption is checked, but we never assume this assumption is correct or checked. All right, good question. All right, so next, normality assumption, right? So since we are testing about the mean, that means for the normality assumption, we just need to check whether the sample size is larger than 30 or not, right? So since our sample size is 225, of course, it is larger than 30, central limit theorem, right? So we say yes. All right, so next, right, after checking the assumptions, we calculate the test statistics, right? So remember at the beginning, we have already figured out the population standard deviation is not given. That's why we have the t-test statistics, right? So we have the formula that the t-test statistics equals to x bar minus mu 0 s over square root of n, right? So we say the sample mean x bar is given, right? So it will be 1, 2, 3, 7, 5 in the question, right? The sample mean is given, right? The mu 0, what is mu 0 here? Mu 0 is our hypothesis value in our hypothesis, right? So it will be 1, 2, 0, 0, 0 divided by s over square root of n. We call the bottom as the standard error, right? So it would be 2415, which is the s, sample standard deviation, over square root of the sample size, right? So we have the bottom as 161. So your t-test statistics is calculated as 2.33. So this is your t-test statistics. Right. Think about the next step. Next step, once you have the test statistics, you find the p-value from the table, right? So now you know this is the t-test statistics. That means we need to go to the t-table, right? So just think about it before you do it, right? T-table, that means you have the degree of freedom, right? So that means we first need to fix our degree of freedom, which is 225 minus 1, n minus 1, 224, right? So this is what we need to find, right? And then find our t-test statistics is between two values, and then we need to go up to find the range of our p-value, right? So this is what we should do next. Right now, let's go to the t-table. This is the z-table, this is the t, right? So we say for the t-table, this is just the one part of the t-table, right? For the degree of freedom, we only have 1 until 49, and then continue to the right 50 until 100. And normally, for a complete t-table, we have 101, 102, and so on. But since we want to limit into one page, then we do not have more details after 100, right? We only have 120 and then infinity. But we are looking for the degree of freedom equals to 224. Which line do we need to go? Which line do we need to focus on? Which line? We say we just find this degree freedom is near to which one, right? Is that near to 100 or 120 or infinity? What is infinity? Infinity will be very, very large values, right? So we say here just the actual topic, right? So we say the t distribution is very close to normal distribution. The only difference is when the sample size is getting larger and larger, the t distribution will be closer and closer to the normal distribution. That means if your n is large enough, then when the n is quite large, close to infinity, then the t distribution will just change to normal distribution. So if you see the last line, you will see very familiar values: 1.645, 1.96, 2.576. What are they? They are actually z stars in the confidence interval, right? So that means if the n is close to infinity, actually the t table just changed to the standard normal table, the standard normal values, right? So in this case, the infinity means the sample size should be very, very large, 2,000, 5,000, 10,000, something like that will be closer to infinity. So in this case, degree of freedom equals to 224 will be more closer to 120, right? Okay, then we just focus on this line. right? In the end, since our t-test statistics equals to 2.33, we just find 2.33 is between these two, right? In the end, we just go up, go up, go up. That means your p-value will be between 0.025 and 0.01, right? So that means what? That means your p-value is larger than 0.01, less than 0.025. Got it? Any questions? Right, so I just use this example, make a large degree of freedom, just in case in your, this case will not show in your exam. I will not make this kind of confusing degree of freedom in the exam, but in your real practice or in the maybe the MyStarLab homework, you may have this kind of problem, right? So I just make a special case, right? So in this case, we have the p-value is larger than 0.01, less than 0.025, right? So that means next step, we can make the conclusions, right? So first, we say before we do the hypothesis test, right, the alpha, which is the significance level, is always given to you. But in this example, I just want to try two cases. So I just tried two significance levels, right? First, we say if the significance level is set to be 0.05, what will be your conclusion? You say the p-value range is from 0.01 to 0.025, right? So this is the range of your p-value. What is your significance level alpha? 0.05, right? Here is 0.02, 0.05 will be here, right? So this will be your alpha. Then the relationship p-value less than alpha, right? So we say p-value is less than alpha, then we reject the null hypothesis. Is that done with your conclusion? Of course not, right? So this will be your conclusion. We conclude that the test provides the strong support for the alternative hypothesis, which means the mean annual mileage for the rental car fleet is greater than 12,000 miles. Right, so this will be your conclusion. You can even skip that's whether you will reject the null hypothesis or not, but you always need to make the conclusion about your claim. All right, okay, so next case. What if my significance level is set to be 0.01? What will be your conclusion? Where is 0.1? 0.01? This, right? So that means all your p-value is larger than the significance level alpha, right? Or you can see this part in the range, p is larger than 0.01, right? So that means what? Your p-value is larger than alpha. We do not reject the null hypothesis. That means we conclude that the test doesn't provide enough evidence to either reject the null hypothesis or support the alternative hypothesis, which means we do not have enough evidence to support that the mean annual mileage is larger than 12,000 miles. Right, so that will be your conclusion. You either have the evidence to support your alternative hypothesis, or you do not have enough evidence to support your alternative hypothesis. All right. Okay, so that would be our example. Any question? Any questions? good. All right, so next let's relax a little bit. Let's do something in the jump. Right, so open your jump, right? And then you should already have this break case dataset. Open it. If you don't have it in the last class, then just click the modules and then click module 1 page. Right, and you should have this data set here. All right, everyone have this data set ready? Yep, everyone got it? All right, so now I want to do a hypothesis test about the mean of the stopping distance. Right, before I do the hypothesis, I want to have a information or summary statistics about this stopping distance. So let's go to Analyze, Distribution. Right, again, distribution. Right, pull this variable to Y, and then click OK. And then you should have this vertical summary. I don't like this direction, so I just stack it. Red triangle beside the distribution, and then click the stack. All right, so this is the default output if you want to learn something about this variable, stopping distance. All right, so it will tell you the distribution of this stopping distance, right? It will tell you the mean of this, we collect this sample, so which is, we have 81 observations in this sample. The mean of this sample is 57.898. Standard deviation of this sample, which is 6.13, and we have a default confidence interval, right? 95% confidence interval, the lower level, the upper level. All right, so now I want to make a hypothesis test about whether the population mean is less than 60. I got the sample mean is 57.89. I want to know whether the population mean is less than 60. So how I can do this hypothesis test? Similarly, right, we just choose the functions by clicking this right triangle beside the stopping distance, right? Just where we find the confidence interval, right? So then in these options, there is one called test mean. Got it? Right, click this test. You will have two blanks that you need to enter. Right, the first one, specify the hypothesized mean. That will be our claimed value we want to test. Right, we want to test whether it is less than 60. Then we just enter 60. Right, next, enter the true standard deviation to do the z-test rather than the t-test. Right, so in this summary statistics table, this standard deviation is about this sample, right? So this is the sample standard deviation. But do you know the population standard deviation in this case? Actually, no, right? So we just keep it blank, right? No entries for the second one, right? Then just click OK. Then you will have this output. You will see that your hypothesized value is 60. Your actual estimate, which is our X bar, right? We use the sample mean to estimate the population mean, so which is this 57.89, which is the same here, X bar, right? We have the degree of freedom n-1, which is 80, and we have, okay, next you will see it is a t-test statistics because we didn't enter the population true standard deviation, right? So we have the t-test statistics. And then we have the t-test statistics calculated. And then here we have three options. three probabilities. Actually, these three probabilities will be the exact p-value for this t-test. Right, so we say the probability larger than absolute value of t will be two-tail probability, right? Two-tail p-value. Right, this one probability larger than our t will be the right tail probability, which is the right tail hypothesis p-value. Right, next one will be the left tail p-value. Right, think about what we did when we do it by find the p-value by hand. We say we have a t-table, right? In the t-table, we don't care whether it is positive, whether it is about the right tail hypothesis or left tail hypothesis. We just use the absolute value of the t-test statistics and then find the p-value in the t-table. But in the JUMP, you have exact p-value for every option for the p-value, right? Either to the right, to the left, or to two tails. Right, so this is about the t-test statistics. But what if I know the population standard deviation? For example, I know the population standard deviation. So I enter the hypothesized, I still want to test whether it is about 60, right? Larger than 60, less than 60, or not equals to 60. But here I know the population standard deviation as 6, for example. I just made up this number. All right, and then click OK. And then the only difference you have in the output is the sigma, which is our population standard deviation, is given as 6. That is what I entered. At the same time, the t-test statistics will change to z-test statistics because the sigma is given. Right, and then we have the z-test statistics. We have again the p-values to the right, to the left, or two tails. Got it? All right. Okay, so for this case, you have the detailed sample, right? Detailed value for each observations in the sample. But what if in our example, we only have the information about sample size, the sample mean, the sample standard deviation, how we can use the JUMP to calculate or compute this hypothesis for us using the JUMP. Again, we go to the help, okay, go to the sample data. And next in this screen, you will see a lot of functions. Just choose the calculators. Right, in this calculators, remember in the last class, we talked about how to get the confidence interval for the mean or the proportion, right? So next, we want to do the hypothesis test for mean or the proportion, right? So in this case, we are testing about the mean, right? So we
Can
just
you show how you got to that window one more time?
Okay, no problem. Help, sample data. Got it? Do you have this?
Got it.
All right, and then at the right bottom corner, you will have the calculators. Click this triangle here, calculators, and then you will have these options. Right? Since in our example, we are testing about the mean, so just choose the option hypothesis test for one mean. Get it? Right, next. Since we do not have the raw data, we have the summary statistics, right? So then click OK. Then you will have this screen that you need to enter all the information, right? So before we enter all the information we have, we need to choose, you have the t-test or the z-test, right? So if you choose the z-test, you need to enter the population standard deviation to the right. If you choose the t-test, the population standard deviation will change to the sample standard deviation. You only need to enter the sample standard deviation, right? So in our case, the population standard deviation is not given. That's why we need to use the t-test statistics, right? And then the first one, the hypothesized mean, which is our hypothesized value, right? 12,000. And then next, sample average, which is our X bar, which is this 1, 2, 3, 7, 5. Right, so next, sample standard deviation, which is our S, right? So it would be 2, 4, 1, 5, right? Sample size, which is 2, 2, 5. Significance level, let's try 0.05 for our first example. And then enter. Right? Okay, now come back to your output here. Right? You will have one more test. Right? For this test, no, not this one. This is about the last example. Right, so once you enter, you have the test result at the bottom, right? So you have the t-score, which is our t-test statistics, 2.33, right? Which exactly with our calculation. Next, you have the observed significance, which is our p-value, 0.02. So in the JUMP, the p-value will be, the exact p-value will be given to you. But in our exam, our example, we have the range of the p-value, right? So this 0.02 is in this range, so no problem, right? So that means if your significance level alpha is 0.05, so of course your p-value is less than this alpha, you reject a null hypothesis, we have enough evidence to support our claim, right? If you don't remember this rejection rule, the JUMP is very sweet, right? There is an option to check to review your decision. So if you check here, it will tell you to reject the null hypothesis. All right, so this is the way how you use the JUMP to make the hypothesis test. So again, you need to know how to make the hypothesis test by hand, and at the same time, once you know what is inside, then you can do something in the JUMP, right? You can edit, you want to do a z-test or a t-test, right? What you need to enter, right? Okay, so you still need to know what is going on for the details. All right, and
Excuse
then,
me.
yes.
So when you were choosing on that like little window that came up, why did you choose population means not equal to hypothesized mean, like two-tailed, instead of doing a one-tailed for greater than?
You mean, a second, I have already closed that. So you mean here?
Yeah, on that left side, like choose type of alternative hypothesis.
Choose this one.
Yeah.
So it doesn't matter which one you choose. Okay, so let's try this. See. Oh, I forgot to talk about this, right? So we have the t-test, the hypothesized mean 12000, and then next the sample average 12375, and sample standard deviation 2415, and sample size 225, significance level 0.05. If you enter that, this is the p-value for the two-tail hypothesis. Right? If you want in our case larger than, that will be greater than the hypothesis mean will be this, right? So your p-value will be half, right? So it will be 0.0104. Good question. I forgot to talk about that. So the default is the two-tail hypothesis, but if you want a right tail or left tail, then you need to choose this alternative hypothesis. It's kind of different with this kind of output, right? So all of these three kinds of hypotheses will be given to you. The p-value will be given to you at the same time. But if you have the summary statistics, then you need to choose the alternative hypothesis by yourself. All right.
Okay.
Thank you. All right. Okay, so we are done with the jump practice, and last topic we want to talk about in this chapter, we want to talk about the relationship between the hypothesis test and confidence interval. Right. So we talked about the confidence interval in the last chapter, right? So we say once we have a sample mean, we allow a margin of error to the left, to the right, and margin of error to the left, so that we have a confidence interval, right? So actually, we kind of have a two-tail thing in when we do the confidence interval, right? So when we talk about the relationship between the hypothesis test and confidence interval, there is a relationship between the two-tail hypothesis test with the confidence interval, right? Because both of these two are two-tailed. Right, so for example, if I want to do the hypothesis test about mu equals to 78 versus the alternative hypothesis is mu not equals to 78. That means what? That means I just want to know whether the population mean is 78 or not 78, right? But before I do the hypothesis test, I have already got the 95% confidence interval for the population mean as 70 to 80. Without going through the 4 steps, without calculate the test statistics, finding the p-values, can you make the conclusion based on this given confidence interval? You reject the null hypothesis, or you do not reject the null hypothesis. Think about it. What does the 95% confidence interval mean? We say we are 95% confident that the population mean will fall in this range, right? So that means the population mean can be 78 or cannot be 78. Can be, right? Because this 78 is inside this confidence interval, right? So 78 is one option for the population mean, right? So that means the mu can be 78. That means you do not reject the null hypothesis, right? So that means we do not have enough evidence to support our alternative hypothesis. Mu can be 78, right? Because this 78 is inside this confidence interval. The other case will be more clear. If I want to test mu equals to 85, mu not equals to 85, I just want to know whether the population mean is 85 or not 85. You reject the null hypothesis or you do not reject the null hypothesis. Think about it. Dominic. Think about it.
You would reject the hypothesis.
You reject the null
The null-
hypothesis,
Yeah,
right?
you would
So
reject it.
perfect. Good. right? So you reject the null hypothesis because what? Because the mu cannot be 85. The largest mu we have should be 80, right? So the 85 is outside your confidence interval. That means the mu, the population mean, cannot be 85. That means your alternative hypothesis is supported. That means you reject the null hypothesis. Right, so without calculate the confidence, without calculate the test statistics, without find the p-values, if you already get the confidence interval, you can use this confidence interval to make the conclusion about this hypothesis. Summary. Right, so we say if the hypothesized value fall outside the confidence interval, then we reject the null hypothesis. That means your alternative hypothesis will be supported. The other way, if your hypothesized value fall inside your confidence interval, then we cannot reject the null hypothesis. Right? That means we do not have enough evidence to support the alternative hypothesis. Right, so I would not suggest you to remember this summary. I would suggest you to think about the whole process because in this semester, you need to remember a lot of things, right? You need to remember the z-stars. You need to remember how to find the p-values. You need to remember the rejection rule, right? I don't want you to remember this because everything will be opposite if you remember it incorrectly, right? So just to think about the whole process. Without this summary, we can still figure out by thinking about it, right? If it is inside, that means we don't know whether, if it is inside, that means the 78 can be one option for the population mean, right? So that means the null hypothesis is correct. That means the alternative hypothesis cannot be supported. Right. The other way, step 85 is outside the confidence interval. That means the 85 cannot be an option for the population mean. That means the alternative hypothesis is supported. That means you reject the null hypothesis. Right? Okay, and the last thing about the relationship is about this 95% confidence level, right? Remember when we talk about the confidence level, we say the confidence level is paired with the alpha, right? So this alpha is in the hypothesis test, we call it is the significance level. In the confidence interval, it's the same alpha. So if we have 95% confidence interval, that means our alpha is set to be 0.05. It's 5%. Right? It's the same alpha in the confidence interval. Right? You cannot make the conclusion about alpha equals to 0.1 with a 95% confidence interval. We don't know about it. We can only make the conclusion for alpha equals to 0.05. All right. We are done for this chapter. Any questions? Good. All right, remember we have a essay assignment. We have MyStylab homework for this chapter. All right, and the last thing I want to talk about is our coming data analysis 1. Right? Can everyone see the data analysis 1 in your Canvas page? Got it? All right, so I haven't decided yet about your groups, right? So I will complete the grouping process within today, right? So I will just randomly assign you into a group with 3 team members, maybe maybe 1 or 2 team with 4 or 2, depending on how many students in each section. Right, so if you have a specific requirement, for example, you want to be grouping with someone as in your apartment, right? That will be more convenient for you, right? Something like that. Or someone is your friend, you want to work with your friend, that's okay. Right? Just email me and let me know. I can just make adjustment, right? And the grouping process, I will let you know on Friday, and also the due date. I will decide the due date after today. All right, and for today, I just want to talk about this data analysis one before you start. All right, so what is the data analysis one? We have a data file given to you, right? This is about 2014 NEISS dataset, right? So I can show you what is that, right? It is a very big dataset, right? So this is the dataset you have, right? You have many variables, right? So in your real data analysis, this is the most common data set you may have, right? You will not be given only one column, give you all the information you need, and then you just go through the formulas and you just find the answer. All right, that will be too simple for you for the real data analysis. Right, for the real data analysis, that means you will have all these informations. All right, and then let's talk about this data set for more details. Right, so you will use this data file, and then I want you to make a random sample from this, from all of these patients. Right, so you will have totally these many patients as your population, right? So that would be 367,492 patients, right? In these patients, I want you to randomly select 1,000 patients. Based on this sample, find a 95% confidence interval for the mean age of patients that are 2 years or older. Right, so that would be too much things for you right now. Right, think about this requirement. So first, you only care about the patients that are 2 years or older. That means before you select the sample, you need to filter the data, right? You need to filter the data only for the patients that are 2 years or older. That means the first thing you want to know the distribution of the age, right? So now let's go to analyze distribution, and then I want to know the distribution of this age to get what are these ages distributed, right? So I don't want this direction, I can stack it. All right, so from this distribution, you will see some interesting thing, right? So you will see the age from 0 to maybe 110, and then you have a little bit strange group which is larger than 200. Can the age of the patients be 200 years older? I don't think so, right? That's not right, right? So why is that? Remember, in your real case, in your real data analysis, any data set will come with, we call it is the coding manual. Right, so what is a coding manual? When we collect the data, right, when we enter the values in the data, we need a coding manual to describe how I collect these data, how I enter these data. Right, so in the page of 7, you will see the coding and data entry. right? You will have all the backgrounds, you have all the introduction about this data set, right? And then you will see that all the variables name here, right? And then next page will tell you for each variable how they enter the data, right? So for example, it will tell you if the date is July 17, 2000, then how they will code or enter the data in your data set, right? So here we only want to know the age, right? We want to know what happened to the 200 and older patients, what happened to them, right? So we say when the date of birth is not available, the age of patient must be entered. For children under 2 years old, record the age in months. To show that the age is in months instead of years, put a 2 in the first space of the age code. That is why, right? Because if you have 3 weeks or 4 weeks, that means it's 1 month baby. That means this patient has the age as 1 month, but since it is recorded as months, I add a 2 in the first space. That means in the data, you will see 201 as this patient's age. That means this patient is a 1 month baby. Right? That is why in your data set, you have what? You have this group, which is larger than 200 as the ages, right? So that means what? That means this group is about the children who are under 2 years old. That is not our research goal, right? So that means you need to delete these values because we only want to focus on we only want to focus on the patients who are 2 years or older. Right, so how to filter the data? Only about 2 years or older. Here I attached a video about just to help you to know how to filter the data. Right, so watch this video before you do the data analysis. Right, so this is the first thing. Next thing, right? Remember, if you have an outlier, you always need to deal with the outliers. You need to delete the outliers. But in our case in here, from the distribution here, you don't have any outliers. These ones are not outliers, right? These ones are just the children under 2 years old, right? So in this case, you don't have any outliers, but if you have one, you need to delete that in the future. Right? In data analysis 2 or the project 1, project 2, you may need to deal with the outliers. All right, so after you filter the data, then you select 1,000 patients from that filtered data. Right, and then as your sample, with that sample, you find 95% confidence interval by jump, not by hand. Right, so and then for finding the confidence intervals and about how to randomly select 1,000 from the whole population, here is another video. Right? I will use another sample, another example to show you how to randomly select the observations from the whole population and then how to get the confidence interval for the population mean by jump. Right, so just I think these 2 videos will be enough for you to do this data analysis, right? And in this data analysis, your job is to repeat this process for 5 different times. That means you will have 5 different random samples, and based on these samples, you need to compute the 95% confidence interval for 5 times. Right, and then here you need to write a 1-page memo. I believe you know how to write a memo in your 100 level courses, right? And just in case, I just remind me that just in case if you don't know how to write a memo, I will attach a requirement for the memo in this data analysis one, right? Later today, maybe, right? And also in one-page memo, and then if you need to attach your output in your memo, then just attach your output in the second page or third page. It doesn't matter, unlimited for the outputs page. All right, so in your memo, you must include these three discussions, right? The first one, discussion about the assumptions, right, for the confidence interval for each, I think just for the general case, right? So you always need to check the assumptions before you compute the confidence interval. Next, once you have the confidence interval, you always need to interpret your confidence interval, right? So that will be the second thing, a clear description of the meanings of the confidence intervals you got. All right, next, the last thing, an explanation of why these 5 confidence intervals are similar and why they are different. Think about it. Before we get these 5 confidence intervals, think about it. You have 5 different samples, and based on these 5 samples, you have 5 different confidence intervals. Right now, give me a reason why they are different, why they are similar. Think about it. Let's just have an open discussion. Any idea? No? Any idea? Let's say why they are different. Why these 5 confidence intervals be different?
If you make 5 different random samples, wouldn't it then maybe you could talk about the spread of the data, the distribution, if it's normally distributed or if it's skewed to any direction? Would that be kind of the explanation you're looking for?
That's good. That's good idea, right? So actually, once you select a sample, if you select another sample, of course, the samples will be different, right? So if your samples are different, then your confidence intervals are based on different samples, then of course, your confidence intervals will be different, right? It will not be exactly the same, right? Your sample means will be different. Your sample standard deviations will be different, right? Okay, now think about why these 5 confidence intervals are similar. Not exactly the same, but they should be similar. Why? Think about what is the goal for the confidence interval, why we are doing the confidence interval. We do the confidence interval to estimate the population mean, right? Okay, does the population mean changed when we collect these 5 different samples? No, right? We are collecting 5 different samples from the same population. That means the population mean didn't change, right? So that means your confidence interval should always around the population mean. So of course your confidence intervals will be similar, right? Okay, so here this will be your data analysis 1. I do not expect that you will have a long memo. Limit to 1 page. Include all of these discussions, right? The assumptions, the description about interpretation about your confidence intervals, and one more discussion, right? That will be your data analysis 1. right? And for each group, I will assign you three team members into each group, and each group you just have I will randomly set a team leader, right? And the team leader should submit your data analysis 1 file to this assignment, right? So only one person sent one submission, and others you don't need to submit the assignment, this data analysis one. Any questions? Right, so I will edit this part right after today's class. Any questions? Be sure to filter the data and the due date. That's a really hard question. So let's say next week we do not have Wednesday's class. So let's say the due date would be more time during next week, I think. Right, I will let you know on Friday. Right, once I complete everything and complete the grouping and make the adjustments if you have any, right? And then I will let you know. Right? And any other questions? Either about the hypothesis test or the data analysis one or anything in your essay assignment, MyStarLab homework, all good? So after today, we'll have something new on Friday, right? So your module 2 page is already open to you, right? So be sure to go through the chapter notes before the class, right? And also be ready for our new material. So of course, we'll go through a little bit slower, but not too slow. Again, you should be ready for the next modules. Right. Any other questions?